Hey everyone, and welcome to this explainer brought to you by Forge College. If you were with us for our last lesson, you know we really unpacked Gulfstream architecture and forwarding mechanics. Well, today we're diving into setting up Foundry workflows. This is all part of our Introduction to Advanced Foundry Testing module. We're going to shift gears a bit. We're moving away from network architecture and zooming right into your personal developer environment. The goal? We're going to build a rock-solid, absolutely bulletproof advanced testing environment. Let's get right into it.
Ah yes, the 6 most famous, and honestly the most frustrating words in software engineering. But it works on my machine. Look, we've all been there, right? You write the code, your local tests pass beautifully, you push to GitHub with a big smile on your face, and then, boom, your automated CI environment just turns into a massive wall of red errors. It's the worst, but today we are going to cure that hair-pulling headache for good. So here's our agenda for today's explainer. 1. The reproducibility problem. 2. The blueprint of a Foundry project. 3. Pinning the toolchain. 4. Writing deterministic tests. 5. Building the CI pipeline. And 6. Verifying identical outputs. Basically, we're going to build a reproducibility machine, piece by piece. All right, section 1, the reproducibility problem. So what actually happens when your tests drift from your laptop to a remote GitHub Actions runner?
Well, to solve that environment drift, we've got to internalize one absolutely core concept, and that is deterministic tests. It means getting the exact same output from the exact same input every single time, without any random external variables. Think of it kind of like baking a cake. If a recipe just says add a pinch of salt and some flour, your cake is going to taste wildly different depending on who bakes it. But if you specify exactly 5 grams of kosher salt and 200 grams of sifted all-purpose flour, you get the exact same cake every single time, whether you bake it in New York or Tokyo. In testing, achieving that exact same output from the exact same input with 0 random variables, that's what we mean when we say deterministic.
Moving right along to section 2, blueprint of a Foundry project. Let's look at the actual physical components required for our Foundry schematic.
Because every good machine has to start with a clean workspace, right? So, here are the scaffolding commands. First, we just make our directory, then we step into it, and finally, we run forge init --template hello-foundry --force. Using this template is super important because it forces a completely clean, interactive free layout. It purposefully prevents any manual setup variations from sneaking in and messing up our deterministic baseline from the very start.
Now, what's really cool is just how beautifully simple this architecture actually is. These 4 specific paths you see here act as the foundational pillars for reproducibility. You've got foundry.toml for your project configuration, the src directory for your Solidity contracts, the test directory for your local tests, and finally, the .github/workflows/ci.yml file, which is the execution script for your CI environment. Okay, section 3, pinning the toolchain. Now we're getting into the most crucial component of our foundry.toml file. So what exactly is pinning? Well, pinning is simply locking in a specific version of a tool, like your compiler, for instance, so that it never changes unexpectedly across different environments. It is literally the only way to avoid the subtle, maddening differences that get introduced by upstream compiler updates. It's an absolute lifesaver.
Inside your foundry.toml, you're going to want to set these exact parameters. Setting salk_version to 0.8.20 completely eliminates compiler-induced differences. And, oh, here's a fantastic pro tip. Setting forge_flags to --no color is vital. It completely eliminates random ANSI text formatting differences in your terminal logs. Because think about it, if your CI system expects plain text but suddenly gets color codes, it might actually flag a failure even when the code itself is perfectly fine. No way we want that.
All right, section 4, writing deterministic tests. Let's shift our focus over to the Solidity code itself.
When we talk about the code, the golden rule for your contracts, like say a basic counter contract, and your test suite is predictability. You absolutely want a simple state. You want no external dependencies, meaning no external network calls or node forks for right now. And you want 0 sources of randomness. So if your test relies on, say, the current block timestamp or some external API that might suddenly go down, well, it's not deterministic, and it will absolutely break your reproducibility machine.
Which brings us to section 5, building the CI pipeline. With our local tools pinned and our tests acting predictably, let's tackle the automated setup.
Assembling the GitHub Actions instructions is actually pretty straightforward. You spin up an Ubuntu latest runner, check out your code, install your pinned Foundry via Foundry up, and then just run forge test. Now, setting up robust, zero-assumption pipelines exactly like this is a fundamental engineering skill. In fact, it's a really key part of the wider Advanced Testing with Foundry courses offered by Forge College. You are basically building a rock-solid foundation right now that you will use constantly.
But the really crucial point here is the installation step itself. Notice, we aren't just saying install Foundry. No, we are installing Foundry up --Q 0.2.0. Zeroing in on a strict pinned version of Foundry like that completely prevents that sneaky environment drift we were just talking about. Your CI runner is now literally using the exact same measuring cups as your local laptop.
And that brings us to the final phase. Section 6, verifying identical outputs. It's time for some quality assurance.
Validation here is a very simple three-step dance. Step 1, you just run forge test-v locally and note the output. Step 2, you push your code to GitHub. And step 3, you inspect your CI logs. What you are looking for here are matching pass and fail metrics. You want to ensure that your local terminal and the CI runner are speaking the exact same language. And when you do that, you get this brilliant magic moment. We have perfectly identical text, 2 passed, 0 failed locally, 2 passed, 0 failed in CI. The test names match, the metrics match, everything matches. This side-by-side comparison right here is absolute proof that our reproducibility machine is fully operational.
Okay, but let's do a quick reality check. What if your CI times out during installation? Honestly, it's a super common developer headache. So here's a quick debugging tip for you. Just increase your runner verbosity, or simply add foundry up --version to your workflows install step. This just lets you peek under the hood to ensure the correct setup actually initialized before any timeout occurred. So to wrap this all together, let's review the 3 core principles we've engineered today to completely cure that works on my machine syndrome. Number 1, pin your toolchain in your foundry.toml. Number 2, write self-contained, deterministic tests that do not rely on external networks. And number 3, create a CI workflow that acts as a perfect mirror of your local commands.
I want to leave you with a final thought to chew on. Are you ready to take this bulletproof, reproducible baseline and expand it into advanced unit and integration strategies? Because trust me, that is exactly the next step in the broader Ethereum dev stacks and frameworks track. If you want to continue mastering these tools and really explore other deep dive Web3 topics, you absolutely need to visit forge.college. Thanks so much for joining me on this explainer. Keep building deterministically, and we'll catch you in the next one.